we're hopping right into the fascinating world of energy systems. The first thing to note is that they lay along a continuum. So in reality, they're all happening pretty much all the time, but which one we're predominantly using is going to be dependent on the intensity of the activity, the duration of the activity, and the availability of oxygen within the cells. The second thing to understand is no matter which of these systems we're using, we're trying to produce a little molecule called ATP, or adenosine triphosphate. ATP is what the body recognizes as energy. Without it, the muscles can't contract and the brain can't think. The third thing to note is that when we use an ATP, it becomes an ADP, or an adenosine diphosphate, and a free phosphate. With that, we're going to get into how we actually go about producing this little ATP molecule. We'll start at the super intense end of the spectrum. So think about the Olympic athletes that run the 100-meter dash. This system has a few different names. It goes by atp-pcr, phosphagen system, phosphocreatine, or creatine phosphate system. For the sake of this video, I'm going to use atp-pcr. This system is one of two that don't require oxygen, but it exhausts very quickly. What happens is the body stores another small molecule called phosphocreatine. And when there are ADPs floating around in need of another phosphate, an enzyme called creatine kinase comes in, breaks the phosphocreatine apart, and attaches that free phosphate onto the ADP to create a new ATP. The limiting factor of this system is that we can only store phosphocreatine in very small amounts. The next system is glycolysis. This can start without oxygen being present. This is the primary system for exercises lasting between 30 seconds and 3 minutes. So think about an athlete running about half a mile as fast as they can. For glycolysis, we either start with glucose or glycogen. Glycogen is pretty much a stored version of glucose. In either case, this is where carbohydrates start to be used for energy. This process is a little bit slower, but it nets in 2 or 3 ATPs, depending on which substrate it started with, and a pyruvate. Without the presence of oxygen, this is where anaerobic glycolysis ends. That pyruvate is turned into lactate and either broken down or sent back to the liver to be turned back into glucose. And here's a secret. Lactic acid isn't actually what is causing your muscles to burn with this type of training. When adequate oxygen is present, we enter aerobic glycolysis, the start of our oxidative pathways. This is predominantly the energy system for anything endurance related. Think 1 mile to 20 miles. This system starts out the same way as anaerobic glycolysis, using glucose or glycogen to produce 2 to 3 ATPs and a pyruvate. However, that pyruvate and some other byproducts enter into the mitochondria. And if you remember anything from high school, it was probably the mitochondria is the powerhouse of the cell. And this is why. A few processes happen in that tiny little organelle. The Krebs cycle and the electron transport chain being the most notable. From these processes, aerobic glycolysis nets between 36 and 39 ATPs. One might then ask, what about fat? I want to burn fat. It's a common ask in the fitness world, right? So, yes, fat can be used as a substrate to produce energy. It is a much slower process, but does have very high yields of ATP. The thing is, at rest, we primarily burn fat. Like 70% of our ATP production at rest is actually fat oxidation and not carb oxidation. The thing is, a lot of media likes to say that if we're doing really intense exercise, that we're going to burn fat. And the thing is, it's actually the opposite. The more intense the exercise, the more glucose, the more anaerobic that we're going to be, or pushing in that ATP-PCR system. So in reality, we're going to burn more fat when we're at rest or at very low intensity cardio. The athletes who use this system are more of your marathoners, especially if they're not fueling throughout the race, and the ultramarathoners. Fat oxidation starts by taking a triglyceride and breaking it into 3 fatty acids and a glycerol molecule. From there, the fatty acids go through a process called beta oxidation to where they are turned into the products that can go into the Krebs cycle and that same electron transport chain that the carbs went through a few minutes ago. The number of ATPs produced depends on how many carbons were in the fatty acids to start with. So we can end up with a range between about 350 and 500 ATPs from one triglyceride molecule. This does, however, require great amounts of oxygen to be present. Lastly, and most rare, and it really only happens when blood sugars are depleted, is protein oxidation. Some amino acids, which are the building blocks of protein, can go through a process called glucogenesis and be turned into glucose and other byproducts that can then go into the Krebs cycle and the electron transport chain for oxidation. However, this is very rare and does not apply to most athletes or people in general who are training. When it comes to training, the majority of our focus is on those first three systems: the atp-pcr, the anaerobic glycolysis, and the aerobic oxidation. For more on training these specific systems, click the video that's here. And if you found value in this video, please hit that like and subscribe to the Iron Darling. Thanks for watching and have a great day. Bye!